So we're given the question, how many grams of O2 are consumed during the complete combustion of 1.00 grams of butane C4H10? So the first thing I want to do is write down what chemical and the amount that I'm given, which is 1.00 grams of C4H10, and what I'm trying to solve for, which is grams of O2. So before I go any further, I know this is a stoichiometry problem because I'm given an amount of one chemical, and I'm trying to find the amount of a different chemical. That's what stoichiometry problems are all about. So whenever we do a stoichiometry problem, we must have a balanced chemical equation. You have to be able to write a balanced chemical equation for the combustion of a hydrocarbon. A hydrocarbon is any chemical that is made only of carbon and hydrogen. Combustion of a hydrocarbon means that that hydrocarbon is going to react with oxygen. So there will always be two reactants, the hydrocarbon and oxygen. And what will always be formed, according to us, is carbon dioxide and water. Always. Two reactants, two products. Now, when we balance it, we do our carbons and hydrogens first, our oxygen last. I look at this chemical equation, I see there are 4 carbons on my reactant side, so I'll place 4 carbons on my product side, 4 in front of that carbon dioxide. 10 hydrogens on my reactant side, so I'll make 10 hydrogens on my product side by placing a coefficient of 5 in front of the water. Now, the only problem with that is when I check my oxygens on my product side, 4 times 2 is 8, 5 times 1 is 5. 8 plus 5 is 13. That's an odd number. And on my reactant side, my subscript of oxygen is 2. So that means there is no whole number coefficient when multiplied by 2 that will give me 13. Now, 6.5 or 13 halves will work here because if we multiply that by 2, we'll get 13. But there's no whole number. And at this level, we really want whole numbers as our coefficients. So that happens sometimes when you're balancing a hydrocarbon. You'll end up, when you're balancing the reaction, the chemical equation for the combustion of a hydrocarbon. That happens sometimes. On the product side, you end up with an odd number of oxygen atoms. So all you have to do to remedy that is multiply everything by 2. So up here I had a coefficient for butane of 1, multiply that by 2 to get 2. Over here I had a coefficient of 4 for carbon dioxide, multiply that by 2 to get 8. Over here, coefficient of 5 for water, multiply that by 2 to get 10. So now when I count my oxygens on my product side, I'll have an even number because I've doubled everything. 8 times 2 is 16, 10 times 1 is 10, 10 plus 16 is 26. That's an even number. And so I can have a coefficient in front of oxygen of 13. 13 times 2 is 26. So now I have a balanced chemical equation. Alright, now let's look at what I have to do after I balance my chemical equation. This is a mass-to-mass stoichiometry problem. I'm given a mass, I'm solving for a mass. Anytime you have a mass-to-mass stoichiometry problem, you have to calculate the molar mass of the given chemical and the desired chemical. So here I've calculated the molar mass for the given chemical, C4H10. Since it's C4H10, I take carbon and multiply its molar mass by 4, because in 1 mole of C4H10 there are 4 moles of carbon. And in 1 mole of C4H10 there are 10 moles of hydrogen, so I take 10 multiplied by 1.01. When I do that, here are my products, 48.04 grams due to carbon, 10.10 grams due to hydrogen. I sum those and get 58.14 grams of C4H10. So this is the molar mass of butane. I also need the molar mass of the chemical I'm trying to solve for, which is oxygen. 2 oxygens, I look on the periodic table, oxygen has a molar mass of 16. 2 times 16 is 32 grams. Now, every stoichiometry problem uses a mole ratio. The mole ratio is always the mole ratio of the chemical we're looking for, the wanted, desired chemical we're looking for, to the chemical that we're given. So in this case, we're given C4H10, so that goes in our denominator. We're solving for O2, that goes in our numerator. And every mole ratio has the word mole in both the numerator and denominator, and these numbers come from the balanced chemical equation. If you look at the balanced chemical equation, there's a 2 for the butane, there's a 13 for the oxygen. So my mole ratio is 13 moles of oxygen per 2 moles of butane. Where did this come from? The balanced chemical equation. So now I'm ready to start my railroad math. Here are my conversion factors, my molar mass of my given chemical, molar mass of my desired chemical, and my mole ratio. I start with what I'm given, 1.00 grams of C4H10, and since I have grams of C4H10 in my numerator, I have to have grams of C4H10 in my denominator, so those will cancel out. The only conversion factor that has grams of C4H10 is the molar mass of C4H10. So that's always going to be my first step. Anytime we're doing mass to mass, the first thing I'm going to do is divide my given by the molar mass of the given chemical. Then I'm going to get to moles of C4H10. The next step is always the same. I'm going to multiply by the mole ratio, which I've already put in the proper form, because I know the given chemical goes in the denominator, the wanted chemical goes in the numerator. So moles of C4H10 cancel out. Now I have moles of O2. The very last step is to multiply by the molar mass of the wanted chemical, which we've already calculated. So if I look at my units, everything cancels out except for grams of oxygen, which is what I'm solving for. And then I can either multiply all my values in the numerator, write it down, multiply all my values in the denominator, write it down, the divided amount, or, because I'm lazy and I don't like to write all that, you can just multiply, divide, multiply, hit equals, divide, hit equals. Multiply, hit equals, divide, hit equals. Multiply, hit equals, divide, hit equals. And then you'll get the same answer, and you don't have to spend time writing it down. But if you'd like to write it down, if that helps you keep track of it, then do it. I'm not attached to how you solve the problem as long as you're solving it correctly. So the final answer here is 3.58 grams of O2. The calculator gives me far more decimals, and when I round to 3 sig figs, since that's what was given, this is what I end up with. So mass to mass will always follow the same steps. Hope this helps.